Hello everybody. In the next video we're going to talk about exponential and logarithmic equations, and also we'll discuss some tricks used in these types of equations. We have many thousands of examples of problems with equations with logarithms, but let's see our first. Solve the equation logarithm in base x from 2 plus 2 from x equals 2 times sine of px over 4. We observe that logarithm in base x from 2 plus logarithm in base 2 from x is greater or equal with this. For example, this one. Plus, we change the base and write it as a sum of two fractions. So we write this, and we know from basic algebra that this inequality holds for every positive numbers. So this one is greater or equal than 2. On the other hand, 2 sine of px over 4 is lower than 2 with equality if and only with equality if and only if sine of px over 4 equals 1. But also here we have equality, so logarithm in base 5 from x is logarithm in base 5 from 2, which is equivalent with x equals 2. This is the only solution. Many problems are solved this way. For example, try to solve the equation logarithm in base x from y plus logarithm in base y from z plus logarithm in base z from x equals 3 cosine of t. Solve this equation as homework, and I expect from you some ideas of other problems and solutions for this and other problems, of course, to improve and enlarge our database of problems of this kind. Okay, let's get further. Let's move on. Solve the equation logarithm in base x plus 1 over x from 4 equals to x plus 1 over x strictly positive, of course. We also note that x plus 1 over x is greater or equal than 2. So log in base x plus 1 over x is lower or equal than logarithm in base 2 from 4, equaling with 2. On the other hand, x plus 1 over x is greater than or equal than 2, so we have equality when x equals 1 of x, which means that x equals 1. Nice. Also try this problem. Logarithm in base let me think. This one, not 9, 27. Okay, equals x over y plus y over z plus z over x. Try this. Thank you. Now let's move on with the next problem. Let's see. We have this equation, logarithm in base 10, we don't specify, from x squared minus 8 times logarithm in base 10 to minus x equals logarithm in base 5 from x squared minus 8 over logarithm in base 5 from 2 minus x. Let's see what options do we have. For example, the right side of the relation above can be written as it follows: logarithm in base 2 minus x from x squared minus 8. Do we see a pattern over here? Well, this one doesn't help us. Actually, so let's continue this. This one can also be written as logarithm in base 10 from x squared minus 8. We change again the base, right? Over logarithm in base 10 from 2 minus x, which is also the product here. Okay, so we have the equation a or b equaling a over b. A times b equals a over b, so b squared equals 1. But let's find out who is b. B is logarithm in base 2 minus x. So b squared equals 1. So x is minus 8. This is our solution. Okay, the last of our problem should be this one. Logarithm in base 3 from 1 plus tangent square of x plus logarithm in base 3 from 1 plus cotangent square of x equals with 2 logarithm in base 3 from 2. This is an easier one because we see that we have to multiply the quantities from the logarithm. So the left side equals with 1 plus tangent square times 1 plus cotangent square equals with logarithm in base 3 from 4. But one plus tangent square besides 1 plus cotangent square equals 1 plus tangent square times cotangent square plus tangent square plus cotangent square, which is greater or equal than 2 plus 2 which is 2 plus 2, which is 4. So the left side is greater or equal than logarithm in base 3 from 4. This gives us the conclusion that 1 plus tangent square of x equals 1 plus cotangent square of x, which means tangent x equals plus minus cotangent square x. For example, x p over 4 is a solution. It's not specified in which interval is located this solution, so we can deduce that a class of solutions should be the set A k for k times p plus p over 4, or 2kp plus p over 4 with k an integer. This is the set of solutions. Okay, now let's try another one, a little more interesting. Solve the equation, the most difficult from all of them. 9 at the power this one times 9 at the power logarithm in base 3 from this one times 9, add the power logarithmic base 3 from the z over 9 equaling if x, y, and z. If we bring at the same base, we have this equality. Now, let's try to bring some inequality here. For example, from arithmetic mean and geometric mean inequality, this is lower than 1 plus logarithmic base 3 of x over 2. This one is lower or equal than 1 plus logarithmic base 3 of y minus 1 over 2, which is logarithmic base 3 of y over 2. And the last one is lower or equal with compared to this. If we sum up those inequalities, we deduce that log in base 3 of x plus log in with the square root of each one, we deduce we have this one, which is lower or equal than logarithmic base 3 of x, y, and z over 2. Okay, so the left side is lower or equal. Let's give another. Seeing this, one, we have that 9 over log in base 3 of x plus log base 3 plus logarithm in base 3 of z over 9 is lower or equal than log base 3 x, y, z over 2, which equals with this one, which is actually x, y, and z and z, but our equation was this one. Our equation was this. Do not forget that. So we have equality in the mean value inequalities. So in the applied AMGM inequality, we have that one equals logarithm base 3 of x equals logarithm base 3 of y over 3, and equals also logarithm base 3 for z over 9, z over 9. So x is 3, y is 9, and z is 27. Okay, this should be enough for now, for the moment, but I'll sure come back with a lot more applications of these tips and tricks, and also with applications of the first derivative. So, to be continued with first and second derivative in studying the increasing or decreasing functions, convex or non-convex concave functions, which are very used in inequalities and solving many other equations with logarithms and so on. Thank you for watching my video. Hope I didn't bore you very much, and good luck.